In our previous video, which I'll link below if you haven't seen it, we discussed IQ signals and how they can be used to represent basically any type of modulation or variation in an RF signal. Not only they can be used to generate any type of modulation, but they can also be used to analyze any type of modulation. So in this video, we're going to explore that just a little bit further with a couple basic modulation types. So we'll take a look at AM, amplitude modulation, FM or frequency modulation, and also talk about how these techniques can be used for single sideband signal generation. Now, to illustrate this, what I'm going to do is use one signal generator to generate some of these signals, and then on the bench here I've put together that same set of mixers that we're using essentially in this configuration here, where we're going to essentially demodulate down to the baseband quadrature components. This signal generator back here is going to be used to generate the modulated RF signals. This signal generator here is being used to generate my quadrature clock, or my quadrature LO, and we're doing a direct conversion through these two mixers. So the output that we're going to be looking at on the scope is going to be just the baseband I and Q signals. These two signal generators have their references locked together, so that way when I set up a carrier frequency for the modulated signal and the direct conversion quadrature oscillators for the mixers, they're going to be phase locked together, so everything will be perfectly stable. That'll make it very easy for us to go examine the IQ signals in a nice stable way. So let's look at amplitude modulation first. So, quite simply again, the amplitude modulation is where the amplitude of the RF signal is modulated by a low frequency signal, typically a baseband signal. And when we talked about the phasor diagram for the quadrature signals, we basically said that amplitude modulation is simply when the I and Q components vary by the same amount. So essentially in the phasor diagram, the length of that vector simply grows and shrinks. Okay, so we don't change phase, we're only changing amplitude and moving that up or down because the I and Q signals are moving up and down. So I've got the signal generator set up to generate an amplitude modulated signal that essentially is in phase with the Q component. Alright, and it's amplitude modulated with a 2 kilohertz baseband frequency. Now let's take a look at what that looks like on the scope. We'll spin around to the oscilloscope. And the scope is displaying both the I and the Q components. And as I mentioned, I've got the phase aligned so that there is no I component at all, so we see the DC on that. And I can see the Q component varying sinusoidally. And if we put a set of cursors up here, we can go measure that baseband frequency right around 2 kilohertz, just as we expected. So that's what it looks like in the time domain. Let's look at the phasor diagram. So we just turn the scope down into XY mode, turn these cursors off, and we can actually see just the vertical bar because we're varying that amplitude up or down. Now it's not real clear that that's really what's going on there, but this does give us a nice way of essentially viewing that vector that we would normally see here. And that vector in this case is just kind of going vertically up or down. If I slow the amplitude modulation baseband frequency down, let's bring it down to say 1 Hertz, now you can actually see the amplitude varying of just that Q component with the I component being 0. Now for the purposes of visualizing that vector or that phasor, let's keep the baseband frequency up high enough so that it looks like a nice solid line. Now I can actually see what's going on. If I vary the phase of this signal, I can actually change the where that vector is, and I'm just changing the phase and then stopping it. And all we're doing now is creating essentially a new vector, with establishing a different phase between the baseband or the RF signal and the IQ signals that we're using to demodulate it. So again, from essentially a phasor diagram standpoint, an AM signal basically is one that we represented by a vector length that is changing, but not necessarily where the phase is changing. So let's take a look at FM. So before looking at frequency modulation, let's first take a look at what happens when you just have a frequency offset between the carrier signal and the local oscillator. And here's one way to look at it. Let's say this is our local oscillator and this is our incoming frequency. What we can see is that, after the first half cycle there's a little bit of a phase slip. After the next half cycle, that phase slip or phase delta is a little bit larger. Next half cycle it's larger again, and so on. So a phase difference looks like a continuous change in phase over time between the two signals. So let's look at what that means in terms of our IQ signal components. So if we look at our phasor diagram, remember that the length of that vector essentially is equal to amplitude, but for frequency modulation we're not going to change the amplitude. But what we said was that the phase is going to vary continually over time. Remember, the phase is represented by this angle here. So what that means is that if you have a frequency offset, this vector is in effect spinning in one direction or the other around this circle, basically describing out a circle because the amplitude is not changing, so it'll be a constant amplitude circle where the phase is varying continually over time. Now, how fast that's spinning around is equal to the phase difference between the two signals. Right? If we go around 360 degrees in 1 second, then that's a 1 hertz frequency difference. If we go around 1,000 times a second, that's a 1 kilohertz frequency difference. Now, the direction that we're going around is basically dictated by which signal is leading, or which one is faster. If the I and Q signals are faster than the incoming RF signal, the vector will spin in one direction, and if the opposite is true, the vector will spin in the other direction. So what does that do to our IQ signal components? Remember, the I and Q components are really the coordinates, if you will, of the in-phase and quadrature components of that vector. So if we picture this thing spinning around here, we can kind of pick some points off and say, well, if the vector was sitting right here, right, the I component will be out here, but the Q component will be right there. As this vector rotates up to here, the Q component advances up to that point, the I component comes down here. And we can continue going around here and actually see that we're tracing out two sinusoids for the I and the Q as this vector rotates around. The other thing that you'll notice is that these two sinusoids are also in quadrature. Where we started off, this is essentially a cosine wave starting at the peak, coming down and going around, where the Q is more of a sine wave starting at 0 and going around. So really a frequency offset is represented in the phasor diagram or by the IQ components as a pair of quadrature sine waves whose frequency is equal to the frequency offset. And depending on which one of these guys is leading, which one is essentially occurring first, dictates the direction or the frequency offset. So let's take a look at those signals. So again, here's our amplitude modulated signal at a basically phase locked to the LOs. What I'm going to do is now introduce a 1 hertz frequency difference between my modulated RF signal and the IQ signals, the LO signals. And you can see what I'm doing is causing that phasor to rotate at a once per second rate. That's because we have a 1 hertz frequency difference between my quadrature local oscillators and the RF signal. If I make that a 2 hertz difference, we'll rotate twice a second, 3 times a second, 4 times a second, and so on. So that's essentially a frequency offset is represented by essentially spinning that vector around, or essentially a IQ sinusoid, a quadrature sinusoid for the I and Q components. So this spinning vector is representing just a constant frequency offset, from the LOs. Now, of course, FM means that we're varying the frequency as a function of our baseband signal. So if I take and bring that frequency offset back to 0, and I change my modulation type from, let's change it from AM to FM. Now what we're seeing, I generating an FM signal here that is got a 1 hertz baseband frequency. So I'm spending essentially a half a second spinning in one direction where the carrier frequency is higher than the local oscillators, and then the other half a second spinning in the opposite direction when the carrier frequency is below the local oscillators. So obviously if I speed up the baseband signal, this would spin so fast that you wouldn't really be able to see it. So I purposely kept the baseband frequency very low so you can see the effect of that vector spinning in either direction for an FM signal. Now, of course, what's happening is when we're getting that reversal in the spinning of the vector, what it really would represent if you looked at it in the time domain is that, in one case the Q signal is going to be leading the I, and in the other case the I signal is going to be leading the Q. So by essentially reversing that situation, we can basically, when we modulate a signal, create a positive or negative frequency offset. So one way to think about that is if I have a pair of sinusoids in quadrature, if I take one of them and I invert it, it essentially makes it, it look like the other one is leading. So if this guy was leading and this one, but then I inverted this signal, it would look like this signal is leading. So inverting a sinusoid is just like adding a 180-degree phase shift. So let's take a look at that on the scope. So I'm back at the case here where I've just introduced a 1 hertz frequency offset. And so we're seeing essentially that vector spinning around at a 1 hertz rate. Now what that represents again is that the carrier frequency in this case, say, is above the local oscillators. Now if I simply invert one of the quadrature oscillators, basically introduce a 180-degree offset to it, I can essentially make, reverse which of those two signals is leading. So if I dial in a 180-degree offset into one of those, now we can see the vector spinning in the opposite direction. So when it's spinning in this direction, for example, this might represent that the RF signal is now 1 hertz below the local oscillator frequencies, and in this situation it's 1 hertz above. So we can introduce a frequency offset in one direction or the other by simply changing the phase between 0 and 180 degrees, and essentially it's just inverting or not inverting one of those quadrature local oscillators. So we can actually change and select whether we want a positive or negative frequency offset by simply changing the polarity of a multiplier. Now this same concept of being able to select a higher or lower offset is also the same principle that was used for the phasing method of single sideband generation. In that phasing method, the audio signal is essentially passed through this 90-degree phase shift network, and that's probably the most difficult thing to do, is to get a good 90-degree phase shift over the entire audio passband that you want to do. And then those two signals are passed into our double balanced mixers driven with a quadrature local oscillator. And then the output, if you add them, you'd get one of the sidebands, like the upper sideband, and then if you subtracted them, you'd flip everything over to the other side of the carrier and get the lower sideband. So this phasing method was actually used for a long time, and still is used today by some people to do upper and lower sideband signal generation, rather than using the filter method where you're filtering away the unwanted sideband in the carrier. Another variation of this is called the Weaver method. And the Weaver method basically substitutes this 90-degree phase shift network for the audio signal with another pair of quadrature mixers. And the audio signal is passed into that, and then those mixers are used to create the audio quadrature signals that are then fed to the next quadrature mixers to create the components used to generate the upper and lower sideband RF signal. So I hope you enjoyed this kind of part 2 video on how some of the basic modulation types like AM, FM, certainly FSK, even single sideband can be generated and, or should say, modulated and demodulated using baseband IQ signals, and how those are represented in essentially the phasor diagram. I think it's a nice convenient way of understanding what's going on with the IQ signals. And in today's software-defined radios, most of the time the IQ signal generation and IQ signal analysis is all done in software. making it very, very flexible to generate and demodulate various types of modulated signals. Anyway, thanks again for watching, and comments are always welcome.